Applications of inorganic chemistry in lead manufacturing. Introduction. Light-emitting diodes, LEDs, have become an increasingly popular light source in recent years, thanks to their energy efficiency, long lifespan, and versatility. While the technology behind LEDs is complex, the basic principle is that when an electric current is passed through a semiconductor material, it emits light. Inorganic chemistry plays a critical role in the production of these semiconductors, as well as in other aspects of lead manufacture. In this article, we will explore the various applications of inorganic chemistry in the production of lead lights. Semiconductor materials. The most commonly used semiconductor materials in lead production are compound semiconductors, which are made up of two or more elements. These materials are typically composed of a combination of group 3 and group V elements from the periodic table, such as gallium arsenide, GaAs, or indium phosphide, INP. Inorganic chemists play a key role in the development of these materials, as they must be able to precisely control the composition and crystal structure of the semiconductors in order to achieve the desired electronic properties. This involves carefully selecting the appropriate precursors and optimizing the growth conditions, such as temperature and pressure, to promote the formation of the desired crystal structure. One important area of research in this field is the development of new semiconductor materials with improved performance characteristics, such as higher efficiency or lower cost. For example, researchers are exploring the use of materials such as zinc oxide, SNO, and tin dioxide, SNO2, as potential alternatives to traditional semiconductor materials. Phosphors. In addition to the semiconductor materials, LEDs also require phosphors to convert the blue light emitted by the diode into other colors, such as green, red, or yellow. These phosphors are typically made up of inorganic compounds, such as metal oxides or sulfides. One example of a commonly used phosphor is yttrium aluminum garnet, YAG, which is doped with rare earth elements such as cerium or europium to produce different colors. Inorganic chemists are involved in the synthesis and characterization of these phosphors, as well as the development of new materials with improved properties, such as higher efficiency or longer lifespan. Encapsulation materials. Another important aspect of lead manufacture is the encapsulation of the semiconductor and phosphor materials in a protective layer. Typically made up of an inorganic material such as silicones, epoxies, or glass. This layer helps to protect the delicate semiconductor materials from environmental factors such as moisture and oxygen, which can degrade their performance over time. Inorganic chemists play a critical role in the development and optimization of these encapsulation materials, as they must be able to withstand the high temperatures and pressures involved in the lead production process without degrading or introducing impurities into the semiconductor materials. Applications of inorganic chemistry in lead production. In addition to the role of inorganic chemistry in the development of semiconductor materials, phosphors, and encapsulation materials, there are several other applications of this field in the production of lead lights. Purification of gases. During the lead production process, it is essential to maintain a clean environment free from impurities that may degrade the quality of the semiconductor materials. Inorganic chemists are involved in the development of purification processes for gases used in the production process, such as hydrogen and nitrogen. These processes typically involve the use of adsorbents, such as activated carbon or zeolites, to remove impurities from the gas stream. Surface treatment. Another important aspect of lead production is the surface treatment of the semiconductor materials, which can affect their electronic properties and performance. Inorganic chemists are involved in the development of surface treatment processes, such as chemical etching or deposition of thin films, to modify the surface properties of the semiconductor.